Okay, so this problem says y equals x squared minus 2. We got a problem. We got the line y equals 2. I went ahead and did it ahead of time for you guys. So, if we're finding the area between the curves, whoa!
That's funny, next year we're going to get the joke.
Yeah, I know. Anybody that sees that's not going to get it. So I want the area there in that blue region, okay? So the tough part of this problem is to say to myself, well, first of all, which function is on top? The line, right? Isn't the line up top? And what's down below? The parabola. And it stays that way, the same way the whole time. We don't have to split it up. Remember in class how we did from like here to here? This was on top minus this down below. Then this was on top minus this down below. Now it doesn't matter. But the hard part here is to figure out, what are my limits? What is my domain? What is this value here? And what is this value here? The intersection point values. Again, take a look, people. Take a look. I want to know this intersection and this intersection so I know what my x values are. So when I do the integral of the upper function minus the lower function, again, remember I have to do the integral of the upper minus the lower. Upper is 2. That's the horizontal line. The lower is x squared minus 2. But I need to know my limits of integration. So from where to where? So as Christian said, we want the x coordinates of the intersection. Now, we did this on the calculator in class, and you can go ahead and try and find it. But it's very easy to do by hand. Do it by hand, please. I can see already it's 2 and 2, or 2 and negative 2. Okay, how do I know this? When you have intersections of functions, they are what? Perpendicular. When functions intersect, what are their values? The same. So set the values equal. Wow. So set this equal to this. This is what we're going to do today, really. This was leading us into today. So you could have, and I allowed you to use your calculator in your homework last night, or the other night. But now what I want you to start doing is thinking about where do they intersect. So set them equal, please. Move the 4 over, please. When I take a square root, how many answers do I get? Plus or minus, right? So what are my limits? Negative 2 to 2. Now, Christian, do I care about what the y values are of the intersection? I don't care a bit. I really don't.
What's the hash value?
The y value? Well, you could just plug it in here or know that it's 2 from that. Absolutely. But again, it doesn't matter, right? Karen's absolutely right, guys. The y value is definitely 2 because it's on the line y equals 2. So these will definitely, this point will be 2, 2, and this point will be negative 2, 2. But the y value doesn't have an effect on the problem. That's what I'm getting at. So please integrate from negative 2 to 2.
And you're doing the lower one?
It's always the upper one minus the lower one. Upper minus lower, upper minus lower, upper minus lower. Please tell me what you get here. Do it by hand, please. You can check on your calculator, that's fine, but do it by hand, please.
In the textbook, there has they had some problems with like respect to lines, integrated functions, but
You're talking about volumes or in the area part?
in the area part,
This is my sister. What would you like my opinion? So she says, this? My sister's like, would you like my opinion? No, I would not like your opinion. Because I'm
Are you looking at the, did you look at the notes or the examples? So the examples that they put that they solve, right?
Oh, I mean the
I didn't see it, yeah. Really? Must be on the previous page, the next page.
I'm thinking about it in my head. I need
You can, that's where volumes is.
That's why I said you can volume and his pen.
For volumes, you have to integrate.
Two extras, the thing I'm gonna get, you integrate.
It's integrated.
Okay.
Wait, what do you mean? You got the.
If you want, if you want to
Right,
figure it
right.
this way, you
But
can
it's
say, okay, what's the upper
included.
function, function on the right, what's the lower function, function on the left, and you can integrate the lower limits, the upper limits, looking at
What you
it.
do? What you do?
You're turning your axis so you can just see them.
4x and
Lower and upper. I'll explain that, sure. I agree with you.
Yeah, the negative.
Yeah, I know that. I know
Negative inside.
So maybe at the end of today after school, I'll go to that point. It's a good thing to do. All right.
Ma'ams.
All right, so
I say ma'ams.
guys, I would simplify before I integrate, wouldn't you? Look at the integrand in the inside. 2 minus x squared is 2 minus x squared minus 2. What's minus a minus? Positive. So this is really 4 minus x squared. That's what I'm really integrating right now. Okay, now take the integral if you'd like. Again, this 2 minus negative 2 is 4. The negative x squared carries down as the negative x squared. Now you can integrate this. This will become 4x minus x cubed over 3. Okay, evaluated from negative 2 to positive 2. Good?
Yeah. If you oh.
Give you what?
No, I was gonna say, is it correct to put like 4x minus x cubed over 3, the dashy line to like negative 2 and minus, no, to 2 and then minus?
Yep, that's fine, Kenny. I see you do it all the time. That's great. Absolutely. And that's how some textbooks write it. Did you see that somewhere else?
Yeah.
Yep, that's fine. What Kenny is saying is this, guys. You know how you have to evaluate the upper limit, and then you evaluate the lower limit, and then you subtract the 2? He writes it like this. He writes it like this. I don't know why I said that twice. I have no idea why I said that twice.
You did said that twice too.
I did, you're right. All right, that's what Kenny does. That's fine. This is pretty much, you done it also, sorry. He's saying take the 2, plug it in, take the negative 2, plug it in, and subtract your answers, which is exactly what we do for integration. Okay?
Yeah.
So you get, well, I just do it in my head. I don't write it out like this. That's what I'm saying.
Yeah.
See how he writes it like this? I don't even show
The
that.
step that you did up there so that I don't get it like mistaken.
But I skip the step you write here, and I write it actually shorter. See what I'm saying? I'm using this one compressed step and then 2. It wasn't a diss. I'm trying to help you for time. That's all. So 4 by 2 minus, well, let me just put in the numbers, right? Can we do this by now in our head?
Yeah.
4 times 2 is 8. 2 to the third is 8, so it's 8 minus 8 thirds. Negative 2 plugging in is going to be a negative 8 plus 8 thirds. Okay, plus 8 thirds, because take a look, this is going to be negative times negative 2 cubed is negative 8. Negative negative is positive. So, if you look at this kind of a problem here, what is the definition of subtraction? Adding the
Difference.
opposite. Let's use the word opposite there. Opposite. So watch this. Ready? Plus, plus, minus. Now, aren't these identical actually?
No, they're not.
They absolutely
I
are.
know what you're talking.
Why are they identical? Who can figure this out?
Because
Because they're equal to each other.
if you split it in half, then it's symmetrical.
Thank you. Symmetry. Look at the symmetry, people. If you go from negative 2 to 0, isn't it that half really? And then from 0 to from 0 to 2 is that half. A parabola is symmetric if there's no horizontal shift. That's why those numbers turn out to be the same. Right? 8 minus 8 thirds. Rewrite 8 as 24 thirds, please. Now, do I have to really do this twice?
Yes.
No. What can I really do instead? Since they're the same, get rid of this half and just put a 2 out in front over here. Okay, think about it in your head. Since these things are identical, you're going to really be adding them. 24 minus 8 is 16, so it's 2 times 16 over 3, which is really 32 thirds. Your book tells you 10 and 2 thirds as the answer for that one. Okay? So again, depending on what you did there, you'll see a different answer. Doesn't matter what form it's in, look at multiple choice. That's number 15 from your homework. I'm going to leave number 16 for you. Let's look at number 17. Again, we're just going to really go through examples right now, okay? That's what we're going to do here. Y equals 7 minus 2x squared. Y equals x squared plus 4.
Nobody says
All right, I want someone to lead us through this. I'm not doing it. Someone else. Let's actually ask for a volunteer first.
Why?
No,
volunteer, I know him, Jack.
How about a volunteer to come up and draw a sketch? Okay?
We know how to be Christian.
Kenny, I want the first one in red and the second one in green.
Well, as a approximation.
No, you haven't. No, because you broke your.
Yeah, oh, of course. The sketch.
I mean, like,
Sketch.
Exactly.
Yeah, it's a sketch. So then.
And please don't yell at him or anything until he's done.
Can I show them the graph?
No one yells.
Check on your graph. You walk
I
back.
know you don't want to see the graph.
Yeah. Okay.
It's so nice this week outside.
Sally was looking inside.
No, it's really nice out.
Yesterday was cool.
The sun and cool weather.
This weekend wasn't that nice though.
One day was.
I was freezing.
Saturday was nice. It was a little chilly, but it was nice. I played some golf.
Play golf?
Played real well. Yeah, this weekend.
Oh my god.
You're not.
You are the guy. You're
You
the
are the
person that I thought you were. I mean, I thought you played golf, but I wasn't too sure.
You are the guy I thought you are.
Right.
It's quite the statement. Deep. So, with this kind of a problem, clearly the parabolas are inverted of each other, right? And that's the first thing I was hoping Kenny would notice. You see that this has a negative a value. Negative 2 means that it's opening down with a y-intercept of 7. That's the y-intercept of 7 up here. Well done. Second one, opening up with a y-intercept of 4. There's the 4 right there, and it's opening up. So, your sketch is what you want to start with.
Yeah.
The area between the curves, what shape is this?
11.
Yeah, or maybe a football? See,
Football's not a shape.
what object does this remind you of? You're right, what object? Oh, football, good idea. Hey Arnold's head. You know what?
Can we just continue the problem? What is it? Oh my god. Are you serious? That's definitely in the description. That's like Jasmine. Jasmine? Oh, it's Christian too.
I don't know what you guys are saying.
Afro guy.
Gerald.
Mr. Harold. Why?
All right, so one of the things I'm gonna have you guys do eventually is a project with volume where you take actual objects and have to fit it. So if I were to figure out the area of Arnold's face, I know. What can I say the lower half is approximated by? This lower part here. What kind though? What could it be approximated by? A very wide parabola, or what else? I can hear you. Hemisphere. The top half maybe you could look at part of a circle, but the bottom is a very wide parabola. I could really approximate it with a line, really. You know, it's like a little bit off, right? And then what would the upper half be? That's a parabola, isn't it?
Yeah.
So if you were given a graph and you were able to figure out this coordinate, so like this one here, I would say, if I were given this a graph, I would say that this line is the line y equals 2. I would probably say that this curve up top is,
I enjoy watching cartoons, man.
let's say this is y equals negative 1/4 x squared plus 6. That's what I would approximate those to be just by looking. So if you want to find the area of Arnold's face, you would take the upper one minus the lower one, find the intersection points, his ears, okay, find the intersection points here and here by setting these two equal, that's all. Okay, later on what I'm going to have you guys do is a volume problem like
Can we
this.
do the Afro guy looks like
Okay.
Christian?
That's a
So we do it after too?
The Afro guy looks like Christian.
What is his face shape though?
I thought it was face shaped like
Go
one
back.
face shaped
We
like
should do that.
a
An
cylinder.
Afro guy right there.
Oh, his hair though.
A cylinder.
Like here?
Yeah.
Christian crying.
Why is that Christian?
He has small ears.
Where did it go?
Again.
Christian doesn't even have emotions.
Yeah, Christian, this one would have to be like what? A cylinder here. But then we go to volume. Maybe we could do his hair as a volume project. This guy's hair.
I'm so excited. I'm sorry.
Eventually, we're going to do this, though. I want you to get an idea of fitting curves. Anyways, sorry. Let's take a look at this one now. So, if I want to find the intersection, what do I do? Without a calculator? Without a calculator now. Good. Set them equal, please. So we got 7 minus 2x squared equals x squared plus 4. Again, I'm finding the intersection algebraically. That's why this is different than last class. Last class, you're able to do it on your calculator. Okay? We don't need to call it out. You guys can solve this all by hand, please. Okay? Move stuff around.
Because we're cool like that. Yeah. You're cool. Are we cool? We're cool. We're not cool. No.
Why do I get 2 answers, guys?
Because
Yeah, and why else? Look at the graph. Have an intersection on there. 2. Now, do I care about the y value? No, I don't. So simply do this. Oops. Okay, just put your x values there. That's all that matters. So now we do the integral of the upper minus the lower from -1 to 1. Okay, from -1 to 1. What will it be? In this case, what's the word? Symmetrical, or the same at each side. Very good. Notice, these graphs have not been shifted left or right at all, have they? So a parabola is always symmetric, thus the axis of symmetry. Remember from earlier? So here, if you find the integral from -1 to 0, or from 0 to 1, you can just find this integral, and then double it if you wanted to. Okay, so I can write it this way. Which one was the upper one? Let me look back. 7 minus 2x squared. You guys, stop focusing on him. I know I shouldn't maybe distracted you there. Regain your focus.
Just studying.
So, this is my actual answer, or this is what I want to do. I want to do the upper one minus the lower one from -1 to 1. Or I could have done it from 0 to 1 and put a 2 out front and kept the same in there. Or I could have actually done it from -1 to 0 to get the left half and put a 2 out in front of it. So I could have done this, or I could have done this. I want you to understand the idea of symmetry. Okay? Yeah, well, there's 3 possibilities. 1, 2, 3. I'm sure you can think of other ones too.
Yeah, I think it's like.
All right, so to do this integral in blue, can I get a recommendation what I should do to start? Simplify. Don't integrate it first, guys, because then you're going to have all these terms. Simplify. You're going to have a 7 minus 4 is going to give you a 3. So I'm using the first integral. I'm not using the other ones. So integral from -1 to 1. Again, 7 minus 4 is 3. Negative 2x minus x is negative x squared is minus 3x squared. Again, negative 2x squared minus 1x squared is negative 3x squared dx. Ken?
I have a question. What do you call it? You know how we equal the y values? Is that only because of parabolas or only because they intersect?
Because they intersect.
Yeah.
If you're finding the area between two curves that intersect and you're using intersections as your domain limits, then you find those intersections with the x. If you're given a problem like you did in class the other day, where you're just given a domain like 0 to 5, you got to actually look at the graph and see which one is above which. The way we did it the other day is the tougher way, actually. This is actually easier, it's just that it's by hand. The way we did it the other day, a lot of people forget that either the upper and the lower functions switch. Remember that whole thing? So if we had a graph from the other day, we looked at two functions, one of which looked like that, and one of which looked maybe like this. And if we wanted the area between them, it's the area here and the area here. Okay, if we were getting the area from 0 to C. Okay, and which one's above on the left side? The green one. So you'd have to do f of x minus g of x. But then here we'd have to do g of x minus f of x. Okay? So it's the same thing we did last time. We're doing the exact same thing. But last time we had to find the intersection. We called this B or something, or we called it C. I forget what it was. But you have to do the integral from here to here, upper minus lower. Then do the integral from here to here, upper minus lower. And we added them together. We did all that work on the calculator. Now we're given problems that ask us to find the area between the curves, and thus we're looking for this region in here. Okay? We're looking for that region. All right, so let's integrate and get an answer quickly. Oops. If I integrate, I don't need the integral sign anymore.
I'm just going to get all my college books on the board.
Oh, you passed it.
What did I do?
I'm slapping my mom with my
Right.
applications. It's funny.
Plug in, please. Kenny, stop talking.
Can we skip a step?
Absolutely. Plus.
But you find it on one side.
Yes, exactly. So this is the area on the left side, right? So we're thinking about it. It's like the area on the right side. That's why it comes out to be 4. So if you had found the integral the other way, if you had found the integral here, you'd have gotten 2 as your answer. You got 2 as your answer here, but double 2 is 4.
Wait, why do we put 2 again?
Okay. Why did I put 2? Because I asked you guys if you were to integrate this function and only did the left-hand side. It's double to get the whole thing, right? So when we're integrating from -1 to 0.
But why do you do it twice though?
No. It's equals, Kenny. Those would equal 2, and then you'd have to double it, so you would end up getting 4 as your answer. I'm saying that the integral on the right side is 2. The integral on the left side is 2. So when you double it, you get 4. That's also verified down here. Okay?
That's only because it's symmetrical.
Technically, yes, assuming it's symmetric. Let's look at an example that's not. Again, if it's symmetric and it makes it easier, do it. But if it's not symmetric, like 5x squared plus 2x plus 7, it's going to be on this side over here. So it's not going to be symmetrical on both sides of the axis. Okay? Yeah, but if you notice that, especially when you're graphing, you see that? Yeah, just do one side and then flip it over. All right. What about... Number 18.
First thing, I'm not a Brit.
Number 18. The last one was number 17. All right, so how about this problem, guys? How about this problem?
You're evil.
About this problem, synthetic.
Alright, so we got a quadratic, we got
Synthetic. Couldn't you?
Well, am I asking to find the roots, Kenny?
Oh, yeah.
No. You need the intersection, right? Before you graph it, though, before you graph in your calculator, find the intersection by hand, please. It's not hard, and you'll see why. Set them equal and find the intersection by hand. Sorry. Find the intersection by hand over here.
Oh, I see what. Yes.
Move the x over, right? Now, take a look at this problem. It's actually a quadratic, but it's a quadratic of a quadratic. Think about it as a quadratic if you were to factor. What numbers multiply to give you 4 and add up to -5?
4 and 1.
Yes, very good. 4 and 1, both negative. Now, since it's x to the 4th, though, it means I need what here? And what are these both examples of, if I can factor further here?
Difference.
Very good, difference of squares. So how many intersections do I have here, guys? 4. 4 intersections. Okay. But you didn't know if they were real, though, Karen. You couldn't have actually,
I couldn't
right?
imagine.
Karen's absolutely right about the idea of roots. There are 4 roots, but how many intersections are there? There are 4 for sure now. And there could have been imaginary. So here, the hard part is this now.
That's why it's
Here's the hard part, guys. We got to figure out what is actually going on here. What is actually going on?
crazy.
What does x to the 4th generally look like? A W. So let's start by thinking about it as a W. Can we do that? Okay. A parabola would look like this, wouldn't it? So if this had 4 intersection points and it's a W, it's probably going to look something like this. Yeah, sorry, -1. I'm putting a 1 at 4 here. Sorry, 4s are there, and then the 1s are over there, aren't they?
3.
Okay, everybody see this? So what's actually going on over here? Sorry, those aren't the roots. I apologize. Those are not the roots. Should have put the intersection points. Here's my -4 intersection. Here's my +4 intersection. Here's my +1 intersection. Here's my -1 intersection. I do not want to mislead you. I put them on the wrong spot. So when I'm finding the area between curves, how many sections am I going to actually have here?
2. Well, can you have 2 in the sense that, like,
3.
3. And that's the hard part. This middle section right here is my first section, second section, and third section. That's why when I gave you guys problems, I gave you the domain. Because now it's like, well, technically I have 1, 2, 3, 4, 5 sections, right? These other sections go on forever. So technically they exist there, but they're never going to cross again because there's no more intersections. These are the only 4 intersections because we solved for it. So these graphs will never cross again. So this will be an infinite amount of area if it goes on forever. So we don't care about those last 2 areas. We're looking for the area that is enclosed by the 2 functions. These are enclosed. This is not enclosed. It expands forever. Think about it this way. If you go to, like, I don't know, a farm, and somebody owns like 200 acres of land, and you just look out, you don't really see any enclosure. It doesn't look like it goes on forever kind of thing. We're talking about a lot of land. That's like right here. Whereas though, if you're in like the pig pen, don't you see the fences? It's enclosed. So these are your enclosed areas, these three, whereas over here, it would go on forever. It's not enclosed.
So if you're not given limits, does that mean you assume
You assume that these over here, if it said find the area between the curves or find the area enclosed from the curves, it's these three. If it said find the area from negative infinity to infinity, then it was infinite, yeah. Because this area would keep going up more and more. Okay? There might be a limit, it might converge actually, I'm not sure. But the idea here now is to do what? How many integrals? 3. How many sections, guys? 3 sections. So, you have to remember, because they're switching upper and lower, which is the upper one over here? Parabola, right? Then the quartic is upper. Then the parabola is upper again. So we have to do this separately. So let's go ahead and do
Can you
this.
say that the two opposite ones are
Why can we say that, Karen?
because they're the same
This is going to have to be long again.
number, but they're just negative?
Okay, more than that, can you
But
stop
the ones
talking,
that are saying
please?
it's
Come on.
positive and negative.
The question is a very good question. It's absolutely right, but the reasoning is not all there. These are definitely the same on the sides. Because if you go back to your original function, take a look at these values. Aren't they all even exponents here?
Yes.
When there's all even exponents, it means that the function is even. When an even function, when you have an even function, it's symmetric about the y-axis. So that's why it's the same on both sides. And this is also an even function. Had this been like that, it's no longer even because of this odd exponent. But if I had a plus 2 at the end or a plus 3 like this, it's still an even function. Because what is this really? X to the?
0.
And x to the 0 is technically considered to be even. Okay? Even though I know it's not even or odd, but when we're looking at even and odd functions, you consider it under the even category. So that's the reason why this problem is symmetric, because they're even functions. Guys, that's one of the topics that I didn't go over, even and odd, which we're doing during the review. I have like 5 topics I wrote down that I want to make sure we hit on when we review. But they're not so broad that we're going to do total like concepts of them. We're going to look at them in example problems.
Instead of doing three integrals, can we just do like the right, like we cut it, but we.
That's what she just said.
Huh?
That's what she just said.
That's what you were talking about. No, because no,
Just
no, that's what I'm talking about. Something else. Okay, never mind.
Okay, I don't know. I mean, instead of doing all 3, she's saying do it symmetrically and symmetrically.
Okay. But
Okay? So for this one, what's the upper function for the leftmost area here? The parabola x squared, right? So I need the integral of x squared minus the quartic. The quartic was 1, negative 4, 4. Okay? So we take the upper minus the lower, and what are my limitations? What is this coordinate of intersection for the x value? And what is this one? So I go from negative 4 to negative 1. That's that one over there. Now, this part is where we go into this next thing. I don't want to do it again. It's not worth your time. So what do you put out in front? A 2 out in front. And we're done with those 2 areas. Now, the middle one I could split up into 2 different areas, and I could do this half, and then double it, but it really doesn't matter, because it's still one integral. It's the fact that I didn't want to do 2 different integrals. That's why I doubled that one. Okay? But for the middle one, I would just say plus, because we're doing areas, integral from negative 1 to 1, because this is 1 now. I'm not going to split it up. I'm just going to do the whole thing in 1. It doesn't matter. If you want to split it up and double it, that's fine. But now, which is the upper limit? Quartic, and what's the lower limit? The parabola. Okay, so this is going to become I forgot my dx. Nobody called it out. Don't forget your dx, please. All right?
Yeah.
Can I leave it at that? Can we work out the rest on your own at some point? Because it's not worth me just going through this math. This is just integration now. Okay, but remember, you do the whole integral over here, and then you double it. You do not do anything with that 2 until the very end. Integrate it, apply the limits, subtract the numbers, then double your answer over here. Over here, just integrate, apply the limits. Okay, and that's our total area between the curves. I want to try and find a harder one, though. These are good, but there's stuff that can be harder than this.
Please no.
We like the same thing, it's just you have to cut the main.
But they had to find the cosine of that thing, and then
All right, this will be very challenging. We're going to get the cosine in a second. We're going to start with one with a circle. Well, we might just finish this one with a circle. So if you have a function, this is number 25. Number 25.
actually there is. It's just coming up Friday.
Okay? So we got here. Now, the thing about this function is that a lot of people try to solve for y. Because you want to know what y equals, right? That's usually how you graph stuff, right? Okay, but clearly we can see that to get y, we're going to have to take a square root. It's going to be plus or minus, so it's going to be a little bit messy. So I'm going to show you a technique now that I just thought about that helps a lot. I remember this from my class when I was in high school. Just find the intersection first. Don't even graph it. You'll never have to graph this, and I'll explain how you can do it. So let's start by finding the intersection. But I can't set them equal, right? Because there's nothing solved. So what should I solve for in both cases? Either solve for x or I would either use substitution or just solve for y squared. Take a look. If you solve for y squared here, you get y squared equals negative x by moving the x over. Solving for y squared here, you're going to move the x over, you'll get 2 minus x, and then divide by 3. That's what you get for y squared over here. Again, we all see this so far? So I'm moving the x over, I'm moving the x over, and then dividing by 3. So with this problem, I can set these two equal. And this is where rational functions come in, algebra 2. And you know what the sad part is? They were asking me the other day, like, where are you going to use this in calculus? I'm like, you use rational functions all the time. But how could I even explain this without actually knowing calculus, you know? That's the hardest part with younger students. So now what do I do with the 3? It's in the denominator. What can I do with it? Good. Just move it on up or multiply both sides. I get negative 3x equals 2 minus x. Add the x over. So move this x over, you get negative 2x equals 2. What do you end up getting? So, how many times do these functions intersect? Just once. Just once. What kind of shapes do I have here?
Circular? Wow, I don't like. What's it called?
Here, if I were to solve for y, here, I'd have to take a square root, right?
Oh.
Yeah, like this, right?
Like tan?
It's like that.
Not a line, it's not exponential.
But it's like.
It's a curve.
Thank you, radical function. It's a radical
He
function.
was trying to say the shape.
Yeah.
That it makes.
Okay. It's like a parabola rotated
Yeah, that's how
90 degrees. Sorry, I didn't even know you were saying that. So here, if I were to solve this, problem and actually try and graph it, the graph you would get from this graph would look like this. Okay? I only know that because a squared function usually looks like this, but a squared function, when you take a square root, has plus or minus, so it's below. But since this is negative x, I have to use all the negative values because negative will make that a positive. Again, because take a look. When I square root this, doesn't that look like it's imaginary at first? Because you see the negative under there? But if I let x equal negative 5, negative 5, doesn't that become positive now? So this function is defined for all values over here now. That's what this function is really. Over here, though, when I take the square root, okay, it's still going to be negative, right? So it's still going to be on that side of the graph, but it's going to be a little bit funky looking. Let's try and reduce this. We're going to get 2/3 minus x over 3 with a plus or minus. So if I want to graph this function here, okay, which is a little bit different, I'm going to think about the fact that I have a shift. Remember the h and k? This is my h value. K would be on the outside. It's always x plus h minus k. I'm sorry, x minus h plus k. So my shift is negative 2/3. So where this one starts is actually all the way over here at negative 2/3. Okay? Then the slope is going to be much less. So we're looking at a function now that actually looks like this. I'm sorry, it's going to be much wider. It's over 3. Lose my mind. So how many intersections are there really, guys? 2. But how many did we get?
1.
We just got 1.
Means that only one matters. The other one's imaginary.
What's the coordinate of the intersection that we got? Is it the x or the y coordinate? X, isn't it? Don't these 2 points have the same x coordinate really? Aren't they symmetric? That's why it only looks like there's one intersection here. Again, this coordinate is -1 some number. This coordinate is -1 some other number. But they're both -1 as coordinates for x. So there are 2 intersections here. Again, there are 2 intersections. Now, the tricky part, and this is where Christians Christian statement earlier came in, me, you asked about integrating with y, remember? For this kind of a problem, turn your head 90 degrees this way, please. Everybody, take your head, turn your head, look at the picture, and turn it this way. So turn your head and look at this picture like this. What is it? Other way. What does it look like to you? It looks like two parabolas, doesn't it? And they're intersecting, aren't they? So what I'm really thinking about is this. If I solve for x up here, watch what I do. Solving for x up here, I end up getting x equals negative y squared, which is a parabola really, just rotated. If I solve for x up here, I get x equals negative 3y squared plus 2. So really what I'm going to be doing for this kind of a problem is integrating with respect to the y-axis. You're integrating with y. And if you turn your head like this, the point that we care about now is the y value. So we need to figure out those y values. Because now we're integrating, we're trying to find the area here in that entire moon or crescent-shaped region. To find that crescent-shaped region's area, you're really integrating from your lower limit here, turn your head still, to your upper limit over here. Everything with respect to y. So my upper function is the one that was above here. That was this one right here. That would be my upper function. This would be my lower function. So for a problem like this, I am integrating the upper function, negative 3y squared plus 2. Give me one more sec. Minus the lower function, dy. Again, because this kind of a problem, you can't integrate with respect to x. You have to turn your head. So what do we need to figure out are the upper and lower limits. So you need to go ahead and plug a negative 1 in right here to find the y value. Well, what's negative 1, guys? What's the square root of 1? So this, plus or minus, right? So this value down here is negative 1, negative 1. This one is negative 1, positive 1. So my limits are going from negative 1 to positive 1 along the y-axis, which is where this problem would actually turn out. Tough problem, I know. Okay, but we're going to talk more about this after school today.